in this section, we are going to look at how you will understand the tripping curve for your circuit breaker. So the understanding of the tripping curve is very important, not only for selection of the circuit breaker, but to appreciate how the circuit breaker actually operates. And of course, like we said, it will help you to select the right and appropriate circuit breaker for your circuitry. So now let us look at the tripping curve, and that is what you are seeing on the right of your screen now. So if you look at the horizontal axis, you see that it is in multiples of the rated current of the circuit breaker, or the nominal current rating of your circuit breaker. Then the vertical scale is your time scale. It's a logarithmic time scale. It is logarithmic because we want to actually accommodate more time on the vertical axis. So if you look at it, you see that it's starting from 1 millisecond, 0.01 second, to about 10,000 seconds. Okay, so that is what we have on the vertical scale. So this is a time current graph now. So let us try to appreciate what we are seeing in the tripping curve of your circuit breaker. Remember, in the last section, we discussed the tripping mechanism of your circuit breaker. We talked about the part that takes care of the overload, okay, condition, or overload fault condition of your circuitry, which is the bimetallic strip. Okay, the heating element of your circuit breaker. Then we also talked about the magnetic element that takes care of those fault current, like short circuit current, that are in excess of the nominal rated current, okay, like 10 times or even 20 times and more of the operating current of your circuit breaker. So these are the two operating elements of your circuit breaker, the magnetic and the thermal, as we discussed before. So the thermal, as we said, takes care of the overload condition of your circuit breaker, and that is what is represented by this part of your graph. Okay, this part of your graph. So if your circuit breaker is, that is, if the circuit breaker is in a circuit that is operating within its nominal current rating or its current rating, you'll see that it will be operating within this region of the circuit of the trip curve, okay, of this graph. So you see that it is between 0.05 to 1. So in this region, the circuit breaker will operate infinitely, no tripping at all. But as soon as you are having current on the line that is more than 1 times the rated current, you see that you start having a condition that can cause the tripping of the circuit breaker. So if you look at your curve now, this area is representing the thermal element, and it is taking the inverse time characteristics, or inverse time characteristics curve. So like we've discussed before, those two tripping elements, the thermal and the magnetic, they operate in different sections of this trip curve. So this part, the magnetic, the thermal element, the bimetallic strip, is responsible for this part of the curve. So you see that as you load the circuit more than what that is the current carrying capacity of the circuit breaker, you see that once you have overload on the circuit breaker will sustain that overload for some time and then cause the tripping of the circuit breaker. Let's assume that we have 2 times the rated current of the circuit breaker. So here on the graph, we have the 2 times the rated current of the circuit breaker. And when you trace it up, that would mean that it will trip somewhere between 15 and 16 seconds. Okay, so when you increase that load, the overload, say to 3 times the rated current, you see that the time it will take to trip has reduced to about 2 seconds. So you see that this section of the curve have the inverse time characteristics. That is, the heavier the current, the shorter the time that is required to trip. Okay, so this is the long time delay simply because some time lapse is needed for the bimetallic strip to get heated up before it can cause the tripping of your breaker, as we explained in the last section of our training. Then this section is the section, as you can see, the electromagnetic trip section is the section that is handled by the magnetic tripping element of your circuit breaker. So when the overload or there is a fault current, okay, that is up to, say, 5 times, as in this case now, 5 times or above 5 times of the rated current of the circuit breaker, you see that the magnetic strength built up around this coil will be strong enough, okay, to pull the plunger, and that will cause the circuit breaker to trip instantaneously. So if it is 5 times the rated current rating, you will see that the circuit breaker will take about, say, 0.03 seconds, okay, here 0.03 seconds to about a little above 1 second, okay, 1 second to trip. Okay, so there will be a short time delay, okay, when it is exactly 5 times the rated current of the circuit breaker. But if it is above 5 times, say 10 times, you see that it will trip almost instantaneously at 0.01 second. Okay, so this part of the curve is controlled by this magnetic element. Okay, so this is the overload section of the curve. You should understand that. And this is the instantaneous trip section controlled by the magnetic element or trip element of your circuit breaker. While this part is controlled by the heating element, okay, heating trip element or the bimetallic strip of your circuit breaker. So when you look at the curve also, you see that we have 2 different curves. Why is this? Why are we having 2 different curves for a singular circuit breaker? Okay, we have 2 different curves because the response of a singular circuit breaker will also be determined, or rather heat, the temperature, the ambient temperature or the temperature of the environment where the circuit breaker is operating will affect the response of the circuit breaker to changes in the current level, okay, on the circuitry. So if you look at this now, remember we said this section is controlled by the thermal element, which is the bimetallic strip, okay? Now, common sense will tell you that if you place the breaker to operate in a hotter ambience, okay, that will a kind of increase the temperature of the bimetallic strip. So the amount of heat that will be required for it to burn will be reduced, okay? So which means that it will require less time when it is working in a hotter environment to trip. Are we getting it? So this curve here represents when you are working in a hot environment, okay, or hotter environment. You see that the time for it to trip, let's assume that we have 2 times the rated current rating. You see that the time for it to trip sorry, 15 seconds, as we said earlier. Okay. Then when the environment is colder, that is the ambience is of less temperature, you see that the time that will be required for it to trip will do what? Will increase, because this element, the bimetallic strip, is colder, which means you need a lot of heat or higher amount of heat energy to cause its burning. And that will mean that for the same amount of current, you need more time for it to get heated up. So if we still look at the 2 times the rated current rating, you see that you require approximately 200 seconds, okay, to cause the trip of this particular circuit breaker when it is cold. Okay, so this trip curve for this particular circuit breaker is when the circuit breaker is working in a hot environment, and this is when it is cold. Okay, so this is the maximum, and this is the minimum, as in ambient temperature. So the area between both curve, okay, is called the tripping zone of this your circuit breaker, which means that during normal operation, this circuit breaker is expected to trip anywhere within this area, which is the trip zone. Okay, but also if you also look critically, you see that it also affects the instantaneous trip time. Okay, so when it is cold, it goes to 10 times from 5 times. Okay, so you should always know this, so that when you are either coordinating your circuit breaker or you are selecting a circuit breaker for your particular circuitry, you need to also know the ambience of the working environment. Okay, so that will make you to have a better informed choice. Okay, so that is what we have on this graph. Okay, so now let us look at something else that is of equal importance also. These circuit breakers, when you go to the market, you will see that they will tell you they are the area where they operate, okay, or the tripping curve guiding their operations, they are always indicated. We shall see that later. So if you look at this graph, what this graph is telling you is that this particular circuit breaker that have this kind of tripping curve, okay, will trip instantaneously when it sees a current between 3 times to about 5 times the rated current, okay, of the circuit breaker. It will trip instantaneously. And this curve is called the B curve, which means that the circuit breaker, okay, that functions, or that this particular curve guides their functioning or operations, they are called the B circuit breaker, or the B curve, okay, is what is guiding their operations. So we also have others. If you look at here, you see that this one can trip or will trip instantaneously between 5 times and 10 times the rated current of the circuit breaker. So this is called the C trip curve, okay? And those circuit breakers that operate within this curve, or that this curve guides their operation, okay, you see the indication that on the face of the circuit breaker that their operation is guided by the C curve or C tripping curve. Then if you go to your far right, you also see that this will trip. This curve shows that this particular circuit breaker guided by this curve will trip between 10 to 20 times the rated current of the circuit breaker. So you need to know this when selecting your circuit breaker, because each of these tripping curve, okay, as it affects the operations of the circuit breaker, have their different areas of applications, okay, that they will be effective. What do I mean? Now, let's assume that you select a circuit breaker that's operating within a B curve, okay, for a very high inductive load, maybe a motor load, or as the input to a high power transformer, okay. You'll see that the starting current, it is possible that the starting current may be up to 10 times or 8 times, let's assume 8 times of the rated current of your circuit breaker, if it is a C circuit breaker. So now, if you take a C circuit breaker, okay, or you take a B circuit breaker for such an instance, what will happen is that since this will be seeing something above this area, around this area, okay, during startup, you'll be having nuisance tripping in the course of the operation of the circuit breaker, which means your equipment will not be allowed to come on because of the wrong choice of your circuit breaker. So if you take circuit breaker like a D, you'll see that it will be able to accommodate those 8 times, and because of this short time delay, 10 times the rated current of the circuit breaker, and then your equipment will be allowed to come on, okay? Then again, if you protect a circuit that cannot tolerate an overload of up to 4 times the rated current of that particular, say a cable now, okay, or an equipment that cannot withstand more than 4 times its rated current rating, okay, you'll see that if you use a C breaker, that particular equipment, since here at this distance 4 times, this breaker will not trip. It means that that equipment will be damaged, okay, before the breaker will even think of tripping at all. And moreover, if you look at the heating element, it will take almost 8 seconds, okay, for it to get heated up and trip. And that time is enough for some internal component of that particular equipment to be destroyed, okay. So in that case now, a B curve circuit breaker will be appropriate. So you see, once it is up to 3, 4, it will just trip instantaneously. And in that particular condition, that is the kind of circuit breaker that we want. So the trip curve guiding the operation of the circuit breaker, it is very important that you know it, okay, so that you make the appropriate selection and protect your circuitry correctly, okay. So if you look here, you will see that all the curves, they are put together, okay. So we have the A curve, we have the B curve, we have the C curve, the D curve, and even the E and the Z, the Z or Z curve, okay. So if you look at this, if the breaker is, this operation is guided by the A curve circuit breaker, it means that it will trip instantaneously between 2 times and 3 times, okay, the rated current of your circuit breaker. B, between 3 times and 5 times the rated current of your circuit breaker. And C, between 5 times and 10 times the rated current of your circuit breaker. And of course, D, between 10 and 20 times the rated current of your circuit breaker. So if you look to the left, this is a circuit breaker, and what you have here is the rated current, okay. This is the rated current, 125 amps. And this C, before proceeding the rated current, tells us clearly the curve that is guiding the operation of this circuit breaker. So here we have that it's a C curve, which is this particular curve. It means that this particular breaker that we are seeing will trip instantaneously when it sees something between 5 times to 10 times this 125 amps, okay. So, which means that if it sees 5 times of 125 is 625. Okay, so between 625 amps and 1250 amps load. Okay, if it sees any current of that magnitude, this breaker will trip. So if you use it maybe to protect a circuit that have a motor load that will trip, its starting current is up to 10 times to say between, let me say 15 times the nominal current or the rated current, okay, of this particular breaker. What it means that during startup, this breaker will be tripping anyhow, okay? So that is what is called nuisance tripping, okay? Tripping when it is not supposed to trip because the load, though very high current that it is seen is a normal load because it is part of the normal operation of that your motor load or your transformer. Then conversely, if you use this same breaker to protect maybe a line, okay, that cannot withstand maybe up to 250 amps, that is 2 times or more than, cannot withstand more than 2 times, or let me say 3 times this 125 amps, okay, which is about 375 amps, okay. At that level, assuming it's a cable now, the cable will be overheated and get destroyed. So before the cable gets heated, it's expected that the circuit breaker should do what? Should trip, as an example now. So if you select a C breaker in this case, you see that it is supposed to trip around this area, okay, between 3 and 4. And that magnitude of current will not cause the C breaker to trip, okay? So before the C breaker will trip, if at all, the cable would have been destroyed. So you see that for us to have a better protection, we need a B circuit breaker, okay, for those protection. So the A circuit breaker is for more sensitive equipment, okay, like electronics loads. You may want to protect them from excessive overcurrent that is up to 2 times the rated current rating. So you just want the nominal to be on the line. So anything above the nominal can cause your breaker to trip and open up your circuit and thus protecting your equipment. So if you look at this chart, you will see a guide to the application of the various circuit breakers, okay, based on their tripping curve, okay, or tripping characteristics. So if you look at it, you'll see that the B tripping curve, breakers that are operating within the B or that are guided by the B tripping curve, they are good for lighting, good for wiring protection, that is the conductor or cable protection, for your control circuits, okay, business equipment, appliances. So if you look at this, you see that we do not have heavy loads, okay, or inductive loads in this area. So the B circuit breaker or circuit breakers that are guided by the B tripping curve, okay, which are these, okay, will suffice, okay, will be good enough. Therefore, DC application, telecommunications, computer equipment, and also for power supplies. Then for the C trip curve, okay, breakers that are guided by the C trip curve, you see that you can still use them for lighting, okay, wiring protection, control circuits, okay. Then you see the addition here for low inrush motors, okay? Motors whose starting current is not up to, okay, 5 times to 10 times the nominal or the rated current of the circuit breaker. Because if it is up to, of course, that will mean that it will cause some nuisance tripping. Are we getting it? Then for the D circuit breaker, you see that you can use it for transformers to handle or to take care of that high inrush current, okay? But most transformers, their inrush current is somewhere between 2 to 10 times the nominal current or the rated current of the transformer, okay? So if it is 2 to 10 times, you see that that is not enough to cause the D circuit breaker to trip instantaneously, okay? So it depends on the inrush current, which are usually stated in the manufacturer's manual. Or you can, if you don't have that, you can probe with your current meter and probe to get the inrush current of the transformer, okay? So with that, you can comfortably protect your transformer, protect your motor that have very high inrush current, okay? So if you go and select circuit breaker in this region, of course, that will cause nuisance tripping. So you need to appreciate this when selecting circuit breakers for your particular circuitry. So understanding of the trip curve and how it affects the operations of your circuit breaker is very, very important.